Hi everyone, my name is Elaine. I'm a faculty fellow at NYU, and this is joint work with Felix Stutz, my PhD advisor, Thomas Wies, and Damien Zufferey. In this paper, we study the implementability problem for global protocols with infinite states and data. Here is an example. In this two-bidder protocol, we have 3 participants, 2 book bidders and a book seller. The protocol commences with the first bidder sending the ISBN number of a book that it wishes to purchase to the seller and the other bidder. The seller responds with a positive integer denoting the price of the book, after which the 2 bidders enter a bidding loop. The loop tracks 2 variables that store the respective last bids made by each bidder, and notice here that the refinements enforce that bids are made in strictly increasing order. So the first bidder proposes a bid, the second bidder responds, and if the sum of the 2 bids doesn't yet exceed the price of the book, then the bidding will continue. At any point in time, the second bidder can indicate its desire to exit the bidding loop by sending a quit message to the seller, which the seller then forwards to the first bidder. Or if at some point in time the bidding is successful, the first bidder, who knows the price of the book, will send a success message to the seller, which the seller will forward to the second bidder, thus terminating the protocol successfully. Writing an implementation for each of these participants individually in a way that is free from communication errors such as orphan messages and unspecified receptions, and also free from deadlocks, is challenging. As a result, the construct of a global protocol has been proposed by multiple verification communities. A global protocol specifies the behavior of all participants' message passing actions from a bird's eye view and synchronously, thus ruling out large classes of communication errors by construction. These global protocols have been studied as early as the 90s in the form of high-level message sequence charts, and are also prominently featured in more contemporary programming language frameworks, including session types and choreographic programming. The natural next step in such a global protocol-centric methodology is to automatically synthesize correct by construction distributed implementations, one for each of the participants in the protocol. As with any synthesis question, one must first address the realizability question, which in our setting we call implementability, which asks, given a global protocol, does there exist a distributed implementation that can inherit all of the desirable properties? We take a formal language theoretic view on protocols and their implementations, which means that for us, implementability amounts to a language equality question. So on one side of the equality, we have the protocol semantics for the global protocol. These can be thought of as generalized symbolic register automata, lifting constraints on the way that registers can be updated as well as on the background theory. So the global protocol features symbolic transitions that are concretized to a potentially infinite set of concrete transitions with register and communication variables instantiated to values from the data domain. These concrete transitions form runs that jointly specify a total ordering of events per participant, as well as a coordination among events from different participants. So for example, the exchange of the success message cannot occur on a run that also exchanges the quit message. From these concrete runs, we obtain synchronous traces, and we split each synchronous alphabet into its send and receive counterpart to obtain canonically ordered asynchronous traces. We then close these asynchronous traces under a notion of equivalence that's specific to our target implementation model, which are communicating labeled transition systems. These generalize Brandon Zafiropoulos' communicating state machines to potentially infinite state devices for each participant that are connected through some network. In our setting, we study peer-to-peer FIFO channels. So this is a network that supports message delay and reordering, but not dropping or duplication. So with this, we can define the implementability question as, given a global protocol, does there exist an implementation in the form of a CLTS such that the language of the global protocol is equal to the language recognized by the CLTS, and moreover, we require the CLTS to be deadlock-free. As an example of non-implementability, Consider if we add the following conjunct to our two-bidder example that requires that the second bidder never place bids that exceed the price of the book, meaning that the two bidders must make non-zero contributions each. This protocol now becomes non-implementable because these two bidders don't have equal access to information. In particular, the second bidder does not know the price of the book and therefore cannot always send bids that satisfy this constraint. In general, when our protocols allow global variables, non-implementability is very easy to run into. And here is a minimal example that doesn't contain branching or recursion, just 3 participants and 3 message exchanges. So participant P first sends to Q an integer x. Q then sends to R an integer y that is greater than x, after which R sends to P an integer z that is greater than x. So because R does not know the value of x, it only knows that x is an integer smaller than y, it cannot exhibit all values of z that satisfy this constraint. Prior work has attempted to address this issue by introducing a notion of known and unknown variables. So a variable is known to a participant if it is either the sender or receiver, and unknown otherwise. Based on this classification, x is known to P and Q, y is known to Q and R, z is known to R and P. However, in this predicate here involving R, x is mentioned, which is not known to R, and therefore this protocol would be rejected as non-implementable. However, this syntactic classification is only a sound approximation, and here is another protocol that admits the exact same syntactic classification of known and unknown variables, yet is implementable. And the only change that I've made here is to change the predicate y greater than x to y equal to x, so that R can indirectly infer the exact value of x through the value of y. In our work, we take a different approach. Instead of analyzing the symbolic protocol directly, we instead look to its concretization to explain sources of non-implementability. And it turns out that for this protocol, non-implementability boils down to the existence of these 2 concrete runs in the protocol. In these 2 runs, the values of x are instantiated with 2 and 3 respectively. Y is instantiated to 4 for both of them. And now z is instantiated to 3. In the top run, R sending to P the value 3 continues to satisfy the protocol, whereas in the bottom run, R sending to P3 constitutes a protocol violation because 3 is not greater than the value of x, which is 3. However, from the pre-states of both of these transitions for R, these 2 runs are indistinguishable to participant R. Yet performing one action on one run constitutes a violation, whereas the other is agreeable. We formalize this intuition into a set of coherence conditions that are 2 hyperproperties. In a nutshell, they say that from 2 locally indistinguishable global states, a participant can either send a message that's permissible from both states and thus continue to not distinguish the states, or it can receive a message that uniquely tells it which of the 2 states it's on, but in the presence of uncertainty, it cannot choose between sending or receiving a message. We show that this characterization is a precise characterization of implementability for concrete infinite state protocols. So the first step in our decision procedure for implementability is this reachability and co-reachability reduction from implementability to these coherence conditions. The coherence conditions are defined in terms of variance of reachability, and from it we immediately derive a finite algorithm for deciding implementability on explicit finite state protocols. In the second step, we define these notions of reachability as least and greatest fixed points over some background theory. This constitutes a mu-CLP reduction. Mu-CLP is a fixed point logic, first order fixed point logic modulo some background theory. And we use this to obtain a symbolic algorithm that is defined in terms of mu-CLP predicates. This constitutes a symbolic algorithm for deciding implementability that is defined on symbolic protocols directly. We use our characterization to derive the following complexity results. For the fragment of symbolic protocols over Boolean variables, implementability is p-space complete. For explicit non-symbolic finite protocols, implementability is co-NP complete. And for the fragment of syntactically defined multi-party session types, implementability remains co-NP complete. The hardness is via reduction from 3 set, and in particular, the condition that dominates the hardness is the second one, that determines whether a particular message is receivable from a particular control state within a global protocol. Finally, I'll mention implications on synthesis. So our results show that synthesis is as hard as determinizing the automata fragment corresponding to the protocol specification, meaning that for all finite fragments, subset construction is a sound and complete synthesis algorithm. And for various non-finite fragments with determinization procedures, they can be used off the shelf directly to synthesize implementations. In conclusion, our paper presents the first sound and relatively complete algorithm for deciding implementability of symbolic global protocols. It improves on prior work along the dimensions of expressivity, completeness, and complexity. And we also implemented our mu-CLP reduction in a CAV paper earlier this year, as well as we mechanized our preciseness theorem in the rock prover. Thank you for your attention, and I'll be happy to take any questions.
Okay, questions, please line up at the mic.
This is very cool work, thank you. I was wondering to what extent your results are modular with respect to the network protocol that you chose. If I want to choose something other than pairs of FIFO queues, can I reuse some of your mechanism, or do I have to reprove a lot of things?
There is a current paper under submission that addresses this question, particularly along the dimensions of network models. So we study abstract network models that include things like global message soup and mailbox, FIFO queues, and so on. And the results partially generalize under certain assumptions on the abstract network.
I look forward to that getting in.
I have a question. Can you imagine a generalization of this framework to handle cryptographic protocols, where one way a protocol might be unimplementable is if it assumes parties can magically break encryption or something like that?
That would require some encoding. So our view on the problem is very extensional, meaning that we can only model message passing behaviors, sending and receiving of a message. So if you could encode violations as message passing, then that would be possible. But we can't guarantee things like local state properties, for example, not directly.
Got it. Thanks. Any other questions? We have 2 minutes left, I believe. Looks like not, so thank you again.